Now, it would have been a lot more different if it was an indole scenario, and that's exactly what an indole scenario looks like. Same problem. You've got a computer desk over here. You have got a dustbin over here. You've got a door over here. You've got a door over here. You probably have a bed over here. And colored means that it's an obstacle. You cannot move over it. So it's it's not really the best thing to do, to hop around, travel and hop around as well. Although you could say that's completely valid. More sophisticated people will move around. So let's say there's another table over here. So these are some kind of obstacles. Now, there's nothing like intersection over here. There's something like a road network graph over here. That's the different ways in which houses are made, and that's the difference between how roads are made. Now, one thing, if you categorize over here, if I need to define the state for this problem, can I do that? Position xy is, of course, a valid answer. However, let's go to the second thing, which is called as a state space. So let's get into the second definition of the state space and see why is that something pretty interesting. So state space. The state space is the total number of states possible in any system, no matter what, how, when happens, as per the assumptions that you have stated. So you already stated that no vehicle will come. So no matter what happens does not mean that a vehicle comes. So a state space, the total number of states that your system can take. So let's take for the indoor-outdoor problem right now. It's clearly the number of intersections. I'm always at either of the intersections. How many total states can the system take? In the worst case, I would be at each one of the intersections some point of time. So my total size or my total number of states possible is the total number of intersections. Now, technically, you also need to say the total number, the state space is all the states or the total number of states which are reachable from the source. Luckily for both the problems, you can go from anywhere to anywhere by at least one road. Who would make an isolated place where nobody can go? Similarly, indoor, who will make a secret cabin where nobody can go? We're not dealing with tax evasions over here where you'd make some secret doors, hallway to some treasure. So let's look at the state space over here as well. Now, can I really define a state space? No, it's infinite. And why is it infinite? Because I could be at 1.1, 2.3, I could be at 1.11, 2.25, I could be anywhere. And therefore, you see that this is currently not a search problem, because even though it is static, you assume nobody moves, you're home alone, lucky you. Even though it is deterministic, you never slip, even though it is fully observable, you can see it, it is currently continuous. And before I even proceed, I have to make it discrete, otherwise there's no point in proceeding. And the way you make it discrete is, of course, you fit in grids like this. and like this. So you say that you divide this entire thing into m cross n grids. So my x-axis can take values from the range 1 to 3 all the way up to m. My y-axis can take values from 1 to 3 all the way up to n. I divide it into m cross n grids, and therefore my state is xy. However, my state space is all the combinations of values so this basically denotes the cross product 1 1 1 2 1 3 1 4 1 5 1 n 2 1 2 2 2 3 2 4 2 n, the size of which is m into n. So now you see it's a finite set of space. It's all the states that you could attain. In the worst case, you could be at each one of them. Now this one technically is not correct because you cannot be on the obstacles. They are unreachable. It's not like a hidden door. The obstacles are actually unreachable. I say I don't have a count of it. So upper limit, let it be mn. So coming along, we stated two definitions for our problem. The state, which is an encoding of whatever changes which drives the agent reaching the goal from the source, and the state space, which is all the states possible, just a set of all the states possible. If you are imagining this from the point of view of a graph, then yes, the states become the vertices, and the state space is the set of all vertices. But now I don't say vertex like algorithm 0, 1, 2, 3, 4, 5. I mean actually an encoding. So for the programs, I usually like state as a class. It has attributes, x position, y position. So class position, int x, int y, or whatever for the different problems that we have. Now, of course, if they are vertices, they've got to be edges, and that is what I call as actions. So actions is a command. So we've abstracted out so many details. So now I'll have to say a higher order command that your agent can execute. So now it's not turn your head by 30 degrees. Now it's move forward one block. Go to CC2 intersections using the straight CC1, CC2 road. Go to the spot 5 tree, which is just ahead of you. So actions are higher order commands. So for this problem, the generic action is called as go to CC1, or in general, go to intersection I, and the robot or the agent or the person knows how to deal with it. This is what I call as my actions. Here, of course, for the indoor scenarios, the actions are more involved. It's up, down, right, left. So you'll have to, the robot will have to plan ahead, ahead, left, left, ahead. That's also how you move agents in a computer program. And the actions are what leads to edges. So the action is what becomes equivalent to edges. Now, let's of course, discuss this beautiful relation between state and actions from this very fundamental thing that I have discussed. Now, every action may not be correct. So, let's take this example. I've got a little graph around over here. Say I am at CC1 and I say give the action go to main gate. Not possible. From CC1 I need to go to the admin building. From there I can go to the main gate. From CC1 there's no road that takes to the main gate. It's a wrong action. Similarly, out over here, which is my indoor example, I am standing over here at this block. I say action right. No, you'll collide. You'll hit the bed. Bad idea. So, these are actions which are illegal or not allowed. And therefore, along with actions, I define a more appropriate term which is called as feasible actions. Out of all the actions, only the actions which are feasible, which do not break the laws of the game, which do not break the laws of the environment, which are correct as per the logic, which are correct as per the rules of the environment, only those actions. So now let's model in the actions using the way that we would like in a little bit more formal way. So let us say I am at CC1. I say my current state is equal to CC1. So my current state is equal to CC1. After that, I apply the action go to main gate. So my current action applied as CC1 is go to the main gate, and my resultant state out of it is, of course, a main gate. Now, this of course will be written as the resultant state is given by the action A applied to the current state S, or the main gate is where I reach if I apply the action go to main gate on the state CC1. Simple enough. And you know that we like a lot of graphics, some nice drawings. I also have a graphical format for it. So from state S, if I take the action A, I reach the state S dash, or from CC1, if I take the action go to main gate, I reach the main gate. Very quickly doing this around over here. So here we follow a naming convention which internationally nobody uses, but of course you know that it makes your programming easier, and therefore I will assume this as the x-axis, this as the y-axis for no reasons. I teach it the other ways, people get mad at me at the lab. So let us say this is 1, 2, of course, I also count from 0. If I don't, people get back. So that's 0, 1, 2, 0, 1, 2, 3, 4, 5. So this is 2, 5. And this is 2, 6. So from 2, 5, if I apply the action right, I get to 2, 6. So it could be made exactly the same way for both indoor and outdoors. That is what I call as the feasible actions. Now, the branching factor I'll tell you what is so specific about the term. We'll just study it without understanding why branching. The branching factor is the maximum number of actions that can be applied from any state. So branching factor is maximum how many actions I can apply. For this example, you can see that maximum outgoing loads are probably 6, 1, 2, 3, 4, 5. Okay, for here it's 5. From any place, I just have one of the 5 loads to choose. More than that won't be feasible. A maximum of 5 would be feasible, so the branching factor is 5. Here from anywhere, the indoor, I can just move left, right, up and down. So the branching factor is 4. It could be less. Like over here, I can only take up, down and left. I cannot take a right, so it's 3. But in general, the maximum is 4. The branching factor is the maximum number of actions feasible that I can take from any state. Now what I will be doing is, of course, that we'll try to solve in some interesting problem using this nomenclature that has been laid down. Before that, let me give in a nice programming touch to it. So I've already said that I do prefer this to be a class. So somewhere should be a class state. And it will have all the state variables. Here, luckily, it's just the intersection name, a string. For the indoor, the X and Y. Every action is typically a separate function. Sometimes the action functions are related, like in the other example of indoor. So, depending upon the implementation, either every action will have its own function, or a group of actions when called with particular setting will make an action function, but this definitely needs to be a function. So that's a class and that is a function. And check feasibility is usually a function either associated with the state or an action or the state action pair, depending upon how you like it. So for the indoor case where you collide, you might say, is the state S dash feasible? And then you say an action is feasible if the landing state is feasible, otherwise an action is infeasible. So these are the three. This is one class and these are two functions that you normally need to make before you start doing in any of the programming assignments. Now, let's very quickly take in a last problem. Of course, the list of problems is infinite and these are classic AI problems. I'll take in one of the interesting ones. It's called as a 8 puzzle problem. So, you've got a picture board like this. You've got numbers 1, 2, 3, 4, 5, 6, 7, 8 and a blank. So now what happens really is that this one is a blank. So I can slide 8 along over here. If I slide 8 along over this line, it leads to a new configuration And numbers are just for us to encode that up. There could be beautiful pictures around. So when I slide 8 all the way up over here, 8 comes here and this becomes a blank. So that's a 8 puzzle problem. And finally what you need to do is you need to get the desired goal configuration, which is 1, 2, 3, 4, 5, 6, 7, 8 blank. That's where you reveal the complete picture. That's goal, that's the souls, also called as the initial state, and of course how you move things around is what makes in the complete problem. So if I need to encode that up, I need to follow the same pipeline. What's my state? Just a 1D, 2D array of these numbers. So what did I abstract out? I abstracted out actually a lot of things. What was the font of this tree? What was the color of this tree? Black. Doesn't change when I go from source to goal. It absolutely doesn't change. Did I abstract out anything else? Yes. I mean, why did I abstract out that 8 could be anywhere in between like this? Same reason. If I move 8 from here, I'll make it reach here. I won't just wait till 8 is in the middle and then think about, do I need to go back? Yes, you may do that. Playing optimally, that never happens. You either make a move full or you don't make it. There's no valid reason to make half a move. So that's what is your state. State space. If you know mathematics, you will calculate it correct. It's 9 factorial. However, only half of them are actually reachable from source. So it's actually 9 factorial by 2. But what I will do is I'll make it 9 factorial only because I don't want to teach you why half of them are unreachable. So let's say it's just 9 factorial. What are the actions? It is up, down, left, right. That is what are my actions. What are feasible actions? Any actions where I have, so like over here, the blank is here. I can move 1 around over here, but I cannot move anything from here around over here. That's not allowed. Here, I can either move 7 here or 8 here. I cannot move anything from here to here. I cannot move anything from here to here. That's what's feasible actions. The branching factor is 4. That will happen when blank is right at the center. You can move 4 items. In all other cases, you can make 1 item less. Now, a few quick definitions again, of course. So, S is called as a predecessor. S dash is called as the successor. You already know that. Action A is not only called as feasible, there is another term that the action A is also called as applicable. The action A is said to be a transition function. So it's said to be a transition function. More clearly, a discrete transition function from the state S to the state S dash. So these are common definitions. What I'll continue next is, of course, to introduction of costs. So every action will have a cost, which is denoted by C of S, A, S dash. The cost in going from the state S by an application of action A to the state S dash, and in this literally sense, in this graphical sense, it's written below the arrow. So above the arrow, I'll write down the name of an action. Below the arrow, I'll write down the cost of the action. Let's say for this problem, I need to minimize my distance. Now, what's the cost of an action? The objective that you are minimizing. So if I'm minimizing the distance, I know from CC1 to the main gate is approximately 635 meters. So that's what becomes the cost. 635 meters. That's the cost written below, or C of CC1, go to main gate is equal to 635. If you know functions, then you know that this can be derived from these two. So I really need not write it down over here. However, I will still, instead of CSA, make it CSA S dash, even though S dash is equal to A of S. Because later we'll see stochastic actions and I don't want to change things then. Here, every step has a cost of 1 and therefore I write down the action cost over here. And of course, you all know graph, you know that whenever all the action costs are equal, or whenever all the action costs are 1, we do not write the action cost. Unweighted graph. It's not that the graph does not have a weight, there is no cost associated. It's just that the cost is all 1, it's all unity, so we just skip writing it. So intentionally it's not written around over here. And then of course, we know that the path cost, which is also the cost of my solution, is the sum of step costs. It will not always be the sum. To be honest, it may not always be the sum. Sometimes you say that you have to minimize in the maximum cost thing that you get. So, like for this example as well, going from one room to the other, sometimes all that you have to say is there's a respectable distance that I need to always keep, and my cost will be the closest that I've ever been to the obstacle. So every step you keep a cost of how close did you get from the obstacle, that's your step cost. Your total cost of the route, I'm not minimizing how much I travel, I'm minimizing how close I get to the obstacle is the minimum of all the step costs. That's how close you got to the obstacle. So most of the cases, simple first example, the path cost, the sum of all step costs, that's also the solution cost that we will be returning to the user. Now, given this example, now what we need to do around is to really start in the process of actual search. And as you would have guessed it right, for any problem. So as a simple case, let us take this 8 puzzle problem. Everything is already defined. Of course, the step cost is all 1 for all CSA S dash, and the path cost is the sum of step costs. So let's take this problem only and let us solve it using the simplest algorithm possible, which is a breadth first search.